Contrastive learning has seen a boom of interest in self-supervised learning techniques, especially in computer vision with papers like SimCLR, MoCo, and Bootstrap Your Own Latent. These learning algorithms map representations of positive keys to be similar and negative keys to be dissimilar. Researchers from UC Berkeley and Adobe Research designed a model that uses contrastive learning for the unpaired image-to-image translation problem, fitting it into the generative adversarial network model. This is where we have a set of source images, like horses, and a set of target images, like zebras, but they aren't explicitly paired with one another in the training set. There isn't a corresponding zebra for every horse image in the source dataset. The researchers use a patch-level comparison, where patches in the generated image that are produced by the generator should be similar to the patch at the same location as in the original image and dissimilar to all the other patches in that same original image. This could be comparing an 8x8 crop of a horse's head with crops of the grass or sky also in the image. This video will explain how they implement this patch level loss, similar to how object detection models use a feature extractor backbone and this hierarchy of spatial resolutions in the feature maps, as well as miscellaneous details in the paper and an exciting application of this model for measuring domain similarity in computer vision, which could be an interesting way to measure generalization difficulty as well. This video will explain contrastive learning for unpaired image-to-image translation from researchers at UC Berkeley and Adobe Research. This paper explores the problem of image-to-image translation. There's been a lot of interesting applications in this area, such as drawing sketches of shoes and then having one of these networks synthesize a photorealistic image of that shoe, or going from a street layout design into a satellite image, or other things like zebras to horses or photos to paintings. This paper is using the generative adversarial network framework to do this translation from source to target domain. And this includes adversarial losses that compare the generated image with the other target images or the source images, or do things like this cycle consistency, where you see how well you can translate from source into the target domain and then back to the source domain, and you'd have some reconstruction loss after you do that series of transformations. So image-to-image translation is this problem of mapping from a source domain to a target domain. But more particularly, we're looking at unpaired or unsupervised image-to-image translation, where we don't have a corresponding painting for the photo, or we don't have a corresponding zebra for each horse image. So we need to learn to translate from one domain into another without paired examples. AVID from researchers at UC Berkeley is a really interesting application of these image-to-image translation networks. In this case, we're looking at imitation learning, which is supervised learning to initialize reinforcement learning policy, where it starts off with some example to copy. So you start off with a human demonstration of how to pick up this cup and put it into the coffee machine. But just trying to do imitation learning from this will be difficult, especially from visual pixel inputs, because of the domain gap. So they use this image-to-image translation network to map it into what it would look like if the robot itself was doing the same task and just copying the video feed with this image-to-image translation network. And then the robot is better able to learn from this initial imitation learning sequence. This paper is getting away from having to do this cycle consistency, where you use a loss that goes from source to target back to source, and then has some L1 or some reconstruction metric that's comparing S prime after it comes out of that mapping with the original image. So the alternative approach to doing the source to target unpaired mapping is by using contrastive learning. And contrastive learning has been super popular in self-supervised learning lately, and so they're adapting it into this image-to-image translation problem. And so what they're doing is they want to have patches of the image, when it's translated, be similar to each other, and this is the positive keys, and then the other patches in the image are the negative keys. And they're going to explore using negative patches from the entire data set as well, compared to using the patches within the same image. So the high-level overview is that the contrastive learning comes from mapping the patches from the input-output, horse to zebra, as being similar to each other in the embedding space Z, and then dissimilar from other patches in the image. The authors are comparing the image patches in the neural network by comparing the different resolutions of the feature maps as they're processed by the encoder in the generator. So these deep convolutional networks, a convolutional network is going to downsample the feature map spatially. So say if you have a 32 by 32 image, a convolution will usually downsample that to 30 by 30, and you also might integrate some kind of pooling that would reduce it to 15 by 15, and so on. So they have this feature pyramid where earlier images that are, or early feature maps that are closer to the original image are higher resolution spatially, and then they get lower resolution as they're processed by the convolutional neural network. So extracting these intermediate features and using them and comparing this with extracting and making comparisons with patches in the image, such as this, say, 16 by 16 patch that captures the horse's head, has been used in a lot of other papers like SynGAN and is really popular and referred to as the feature backbone in these object detection networks. And it's used to extract this hierarchy of features at different resolutions in the neural network and extract and compare these patches. So hopefully this image can further describe how these image patches are being compared. So we have the original image of, say, this horse or this zebra, and we apply a 3x3 convolution on it, and that 3x3 convolution makes up the entry in this layer. Say this is the input and then this is layer 1. This would be the entry at this position in layer 1. So then in layer 2, this entry is now also, there's a 3x3 convolution in this layer, and that would make up the entry in layer 2. But going back to the original image, it makes up this much bigger patch that would now be like a 9x9 patch corresponding to this entry in layer 2, and then so on for layer 3, and so on. So as we extract these features, this feature would correspond to this patch of the original image. This is how we're describing patches and using that term patch. We don't mean, say, taking this 1616 patch from the image and then, say, passing each patch through like a Siamese network kind of thing and then having a comparison just with the patches. Rather, we're looking at the intermediate feature maps of the encoder half of the generator network in this generative kind of contrastive network framework. We also have the generative adversarial network where we have an adversarial loss on the zebra translation. But then we also have now the generative contrastive network half that's looking at contrasting these intermediate feature maps. Contrastive learning is implemented with the patch noise contrastive estimation loss, where we're comparing these intermediate feature maps of the original image X that's in the horse domain, and then Y prime, the zebra image that comes out of mapping from X to Y or X to Y prime, is describing the output or the prediction of the neural network. So you see how we're comparing these different feature maps that vary along this channel axis dramatically. So it's not just height by width by RGB, it's height by width by the number of channels in the convolutional network, which is why it has this rectangle shape and looks longer in the depth wise, because we're comparing these entire feature maps to one another, not just the spatially as if taking out this RGB crop. So then the PatchNCE loss is similar to just doing this n+1 way classification, where you're doing basically a softmax cross entropy loss on the positive patches, and then all the other patches are treated as negative labels. Another interesting detail is noting the overlap between these contrastive learning papers. SimCLR saw a big gain by, instead of just going from F to Z where you apply the contrastive loss, they have a projection head H. And H takes this representation F that's then going to be repurposed for the downstream task like ImageNet classification or whatever you're learning representation for, but there's going to be a separate projection head G that's going to go take the loss of the contrastive learning, info noise contrastive loss, for example. So in this paper as well, they're going from the final layer, whichever patch they extract is also going to go through a multi-layer perceptron projection head to take the loss function and then backpropagate that through these earlier features. And this table from SimCLR shows the difference in performance from taking this H representation compared to G of H, or what the projection head does to that intermediate representation. And you see much better performance with H than G of H. Putting this all together, this is the PatchNCE loss that's used to make the patches in the source and target or generated image similar while making the patches dissimilar to all the other random patches in the image. So making the horse head distinct from, say, the grass or the sky and similar to the zebra head. So this is by doing the softmax of the patch with the translated patch, and you use this temperature parameter to smoothen out these softmax loss functions, and then you normalize that by the sum of all the negative examples. This is the similarity with the positive key divided by all the other keys and the negative keys. So the way that they're going to implement this with patches is they're going to be looping through the different layers of the network. So they're not just going to look at patches at, say, the first layer or the second layer. They're going to have some parameter L that's defining how many of these layers they want to loop through and compare the feature map. So again, they're using this hierarchy of the features and the spatial resolutions of them. And so they can compare the patches at, say, layer 1, layer 2, layer 3, and so on. But these are deep networks, so it could be like layer 20 or something like that. So then what they do is they compare the spatial locations as well. So looping through the spatial locations, that depends on what layer you're on as well. And then they compare the loss function with this intermediate Z code with the Z prime that comes out of the patch on the other side. So the corresponding patch at the same location and at the same layer of the same encoder network. And then they're using all of the elements that are all the other this set S just at the spatial location, excluding this S that's used to do the extraction of the intermediate feature where you're doing this comparison. So this is how they sample and sum this up to compute this loss function over the source and target image. So this is an example of different contrastive learning loss functions that were explored in SimCLR, just to give an example that you don't have to just use this n+1 way classification loss with contrastive learning, and you can also look at some other variants if you're interested in these as well. The algorithm we just described is comparing patches within the same image. So you're looking at patches within the same horse image to get the negative keys. But another approach might be to sample these negative patches from the entire data set of horses. So for example, you might have one horse image where the horse is by itself, another one where someone's riding the horse, and you might extract that patch of the person on top of the horse and then use that as a negative patch to do the contrastive learning with the image that's just the horse by itself. So they use this momentum contrastive learning algorithm, which is a clever way of storing these negative keys where you want to use a large negative batch, and you have this better way of encoding them and using a momentum encoder to have this queue of the previously encoded keys that you use for negative examples. But they're actually going to find that this doesn't work better than just using the keys from the same image. Quickly, I think it's worth mentioning that we're still using the adversarial loss as well, because otherwise the network wouldn't change the image at all. The best solution would be just an identity mapping, and then it's the exact same patch in the positive keys, and that would be the easiest way of solving that problem. So putting these loss functions together, this is the final loss function that's used to train the network in this paper, Contrastive Learning for Unpaired Image-to-Image Translation. We have the classic adversarial, is this image the Y prime, a member of the zebra real images set, or is it a fake image that comes from the generator? So we have that classic adversarial GAN loss in there, and then we also have these contrastive learning losses. So we have the loss with the X, and the X is where we're sampling one of these horse images, and we're comparing the horse image that comes out of it, the X prime or the Z prime, as we map from X into the zebra, and then we compare these features. But we also have the contrastive loss with images from the target domain. And this is like a identity loss because we don't want to have these zebra images be too different from the target set of zebras. So again, this is unpaired, so we don't have an exact match to compare the ground truth Y prime with some other zebra Y in the set Y of all of our zebras. So we're just sampling a random zebra image, and then we're going to do that same comparison to have this kind of prevention of making the generator making these dramatic changes as it goes from horses to zebras or any source to target domain. It might be useful to look at this diagram one more time to describe the way that this patch noise contrastive estimation loss is implemented. So we have the original image X, and the generator produces X prime or Y prime from this X. But now in our discriminator, we look at the encoding layers of the generator and compare the representations as you pass this X through it as well as this Y prime through it. So we're comparing these two representations to then extract intermediate patches and then pass them into the contrastive loss. So it's the discriminator is comparing these intermediate features as you recompute the activations from this Y prime and this X. In the paper, the authors perform ablation studies with these different factors, like the difference between using the patches from within the same image or using some kind of momentum encoder framework of having these negative examples from the entire data set, and they find that using it from the same image is more effective than this memory bank of the entire data set's encoded patches. They also find that it's really important to use multiple layers of the encoder. So not just comparing the patches as a layer 1, we also compare 1, 2, 3, and so on. And then they also find that using this additional term where you're comparing the patch distance with images from the target domain stabilizes the training as well, even though it's a bit of a funny thing because you're sampling a random Y is how I interpreted that this is implemented. So here are some examples of translating these cats into another target domain of cats that come out of this network. This table from the paper shows the results of translating different sources into different target domains, such as going from horses to zebras, or horses to zebras with a more complex horse image, or cats to dogs, or really interestingly as well is these pixel map labels like what you'd use for semantic segmentation into these street view video feeds like what you might see with a self-driving car. So you can see the differences between this algorithm and then a different parameter, hyperparameter ablation based on how you weight the PatchNCE losses with X and Y. And then you can see the qualitative differences with the CycleGAN model as well as these other approaches to image translation. This is a really interesting and impressive translation, especially given that there is no pairing or supervision with mapping from each image into a target image in the training. So in their results table, they also show these evaluations of things like the FID score and these approaches to have some kind of automated metric of evaluating generated image quality. At the end of the paper, the authors present an application of this for measuring domain similarity between two targets of images. So say comparing horses and zebras, or more realistically, comparing the training data set used to train, say, a medical image analysis classifier or a self-driving car or a robotic visual control algorithm, and compare that with, say, the similarity of the test data, and then maybe use that to have a better measure of generalization compared to just some kind of held out test set and just kind of guessing at the splits of trained test, and rather than having some kind of metric where we can explicitly measure domain similarity. So the way that they're showing how this could be used for domain similarity is by taking two query points, this blue point and this red point, and using it to compare these patches as the positive keys with dissimilar keys, and showing what that dot product of the exponential between V and V plus over V minus, or over the sum of all the V and the negative keys, looks like for each of these query points. So you see the blue key, this is what this blue query looks like with the rest of the image, and then this is what the red query, the background, looks like with the rest of the image. So in this visualization, white means more semantically similar and black means less semantically similar. So you see the blue query point is showing that the model has some sense of this is the zebra, these white images, this patch is a zebra, and these other patches of the zebra like the body and legs are also part of the zebra, and they're more similar than the grass background. And the red point, which is in this case on a tree or in this case on the grass, has more similarity with the other grass points and less so with the horse or zebra. And it also, in this case of the tree, has more so with the other tree and less so with the zebra and kind of this dirt in the background. So training this model with the contrastive loss that learns to map these patches together and then also be doing this image-to-image translation is a promising representation learned for comparing these domains and maybe taking some average sampling from the patches and sampling from the images in, say, the train and test set to get some metric of the distance of these vectors that have been explicitly trained to maximize similarity, maximize dissimilarity with negative keys. So this domain similarity idea is really interesting. In this paper, Don't Stop Pre-Training, they're showing that as you start off with this corpus that's used to pre-train Roberta and then fine-tune it into further domains like news, reviews, or biomedical or computer science research papers, the farther away the domain similarity is, the more you stand to gain from doing further pre-training in the target domain. So you get more benefit from going from Roberta to computer science papers than going from Roberta to news articles. And the way that they do this in text is by just doing this vocabulary overlap. So they have these convenient like n-gram overlap or vocabulary overlap. They have these convenient heuristics for doing this in text, but it's harder to do this for images. So this is a promising direction for, or something like this is a promising direction for doing this kind of domain similarity and having some kind of like generalization difficulty metric based on the distances between these domains as you're going from a classifier that's trained on ImageNet and then transferred into like CFAR10 or another one of these like Oxford Flowers or STL10 or the Street View house numbers, all these different image classification data sets that are popularly used. In the famous paper on the measure of intelligence, Francois Chalet describes intelligence as being a function of the generalization difficulty divided by the priors and experience. And priors can easily be interpreted as how much we're using data augmentation or whether we're using, say, convolutions and self-attention or all these little priors that we can inject into the model to make it learn faster, or something like curriculum learning or all these things like meta learning loops and all this stuff as ways to inject more priors into the system and more prior knowledge that would guide it to learn quickly and have more initial understanding of the task. And then experience is just understood as the amount of data that we're using. But generalization difficulty is a tough thing to kind of nail. It could be, frequently we're looking at just doing train test splits where we have the train set and then the test set and they're just randomly split. But we could also imagine maybe some kind of like compositional test where we have these explicit tests like the checklist NLP test that designs all these tests to measure how well the model will generalize to these different kind of linguistic applications like negations and logical consistency and stuff like that. But it could be interesting to look at domain distance as a way of measuring generalization difficulty. Say you have a skin lesion classifier and you measure the distance between the train set and then these other test sets and how well it performs outside of a certain range of domain similarity, or using that just as some kind of signal to get a better sense of the distance between these, or the difference between these train and test sets. So I think it's really interesting looking at this kind of model that's trained to do source to target translation, as well as this contrastive learning loss that is paired with it to approach this domain similarity problem. Thanks for watching this overview of contrastive learning for unpaired image-to-image translation. In this model, we're combining the adversarial loss of mapping the source to target image and then having this adversarial, does it belong to the real target set or does it come from the generator? And then we also have this contrastive learning loss at the patch level, where we're comparing the similarity between patches in the image at the feature map level between the original image and then the generated image. And then we're making it dissimilar to other patches sampled from feature maps in the same image. And the paper shows that it's better to use it from the patches from the same image rather than just encoding it from the entire data set and storing that in some kind of momentum encoded queue, as in the MoCo contrastive learning framework. Thanks for watching, and please subscribe to Henry AI Labs for more deep learning and AI videos.